Hi, my name is Dan Moriarty, and I'm a graduate student at Brown University working with Carly Peters. So I've been looking at the compositional diversity of central peaks within South Pole Lake and Basin. Previous surveys have noted that South Pole Lake and central peaks tend to display a pretty narrow compositional range dominated by low calcium pyroxene. So it's been suggested that these peaks are sampling a homogeneous layer of impact melt or breccia underlying the basin. I've selected 4 large central peaks within the basin to study, to do more detailed analysis with moon mineralogy mapper data. I've developed a suite of spectral parameters that help to characterize the compositional diversity and identify distinct spectral units within each central peak. So we've observed some diversity in the central peaks, which has implications for the stratigraphic layers underlying the basin. So if I've managed to interest you in this work, my poster's in the back room, and I'll be there tonight. Thank you.
And I think we have an appropriate number up here, so in order to stay on time, we'll stay at the 8 together. Thank you.
Hi, my name is Kerry MacDonaldHannah. I'm also a graduate student at Brown University, and one of my research interests includes how near-surface environments of airless bodies affect their thermal infrared measurements of their surfaces. My poster here focuses on a new emission chamber that we have in the RELAB at Brown University. The Asteroid and Lunar Environment Chamber, also known as ALEC, can actually simulate the pressure and temperatures found at the surfaces of the moon and asteroids. So if you come by my poster number 92, we can talk about how we're simulating these lunar environments and the asteroid environments, how these environments affect their the thermal infrared measurements of their surfaces, and we can also talk about how fundamental it is to make these measurements under simulated lunar conditions for the interpretation of current thermal infrared data sets like Diviner and future data sets like OSIRIS-REx. So again, my name is Kerry. My poster number is 92, and I'll be there from 5:30 to 7:30. Thanks.
Hi, my name is Leah Cheek. I'm also a graduate student at Brown. I'm working with Carly Peters. And I've been working on a project recently aimed at constraining the iron content, or Mg number, of the spinel observed by M-Cubed at a handful of lunar craters and basins, and I'm using laboratory near-infrared reflectance measurements of known spinel compositions to do this. And one of the major objectives is to be able to say something about the Mg number of the mafic liquid that would be involved in producing the spinel through reactions with a north acidic country rock. And our approach actually involves synthesizing a suite of magnesium spinels with systematically varying iron content, and then measuring all the run products in the RELAB and looking at which composition most closely relates to the M-Cubed observations. So without giving too much away, I'll just say that it looks like M-Cubed is seeing really low iron spinel, which would require a pretty high magnesium liquid. And if you want more details on that, or if you just want to hear stories about a remote sensing student trying to do high temperature experiments, my poster is, I think, 37 tonight, right behind all the chairs in the back room there. Thanks.
Will Vaughn, Brown University. My poster is about the enigmatic lunar feature Ina. Ina is a 6 kilometer square, 30-meter deep pit with low mounds rising from its floor. Looks like little else on the moon. A number of models have been proposed to explain how Ina might have formed. Maybe it's a volcanic caldera, a field of inflated lava flows, a surface stripped bare of regolith by outgassing. But I think recent LROC-NAC imagery shows that all these models have serious problems. And based on my own geologic observations, I've come up with a model suggesting that Ina is formed by the growth and coalescence of pits, and that these pits themselves are formed by mass wasting into void space left by the sublimation of a volatile, so that Ina is a lunar sublimation terrain. What's the volatile? Where's it come from? Come by my poster, 54, tonight for some constraints. Thanks.
Aloha. I'm Janice Harvey. I'm with Gemini Observatory. I'd like to tell you about another program that was happening over in Hawaii. It's called Journey Through the Universe. It's an education outreach program that has been ongoing for 8 years, and I am so proud to say that NLSI is a partner. I see many of you out here in the audience that have come over and participated in the program, and I look forward for many years to come. It is a program where we have master educator workshops, we have professional development workshops. This past year, just to give you some numbers, we had 72 astronomy educators along with NASA scientists visiting 20 schools. We visited 382 classrooms, 7,660 students. After 8 years, we are seeing incredible results. We are just welcoming anyone who would like to come in and participate. It's going to be in March of 2013. I have a poster. It's number 25, and I would love to talk to all of you about it. Thank you very much.
Howdy. I'm Keith Henson. I'm probably best known for founding the L5 Society a long time ago. I'm retired now, but in the last few years I've been working independently on a project for making power satellites to make sense. To make sense, they have to get power down to less than the cost of anything other way, and the volume they have to do is up in the order of 500,000 tons lifted to GEO per year. In February of this year, I figured out, it just finally dawned on me that if you had one power satellite in GEO hooked to a bunch of propulsion lasers, you could drop the cost to the point where you could indeed get 2-cent power. So the problem is, of course, is to get through that. It's like maybe $140 billion kind of numbers to get to the point where you could do it. But it turns out it's probably worth building one power satellite and propulsion lasers on conventional rockets and then putting it up. If anybody wants to see what I've been doing on this, I have a JBIS paper in progress that I can't post, but if anybody wants one, ask me for an email address and ask for one, and I can send you a copy. It'll let you skeptically peruse it. Thank you very much.
Hi, I'm Tim Livengood from Goddard Space Flight Center, and my local address is poster number 84. I've been looking at using the Lunar Exploration Neutron Detector to get an estimate of the actual quantity of water that is seen in the hydration features that were identified at the lunar terminators a few years ago by epoxy, M-cubed, and so on and so forth, and whether it's really a noticeable amount of water. Since you may not have time to get to my poster because there are so many others, the answer is yes. But if you're unwilling to take my word for it, you're going to have to come by and let me persuade you. So thank you very much.
Hi everyone, I'm Sean from Australia, Sean Moss. I'm just going to let you know I'm a computer scientist. I'm working on a website right now. It's called moonmars.com. That's MOONMARS. It's designed as a collaboration and visualization framework for space research and space settlement. It's not online yet. It's going to be going online in the next couple of days with some very basic social networking features. But the intention is to have a full virtual environment online with a model of the Moon and Mars. And we're going to be building settlements and rovers and spacecraft and putting those in the virtual environment so people will be able to explore the Moon and Mars through their web browsers. So if you think you'd be interested in something like this, you can't sign up today, but if you give me your email address, I'll certainly let you know when it's online. Thanks.
Okay, thanks again to our speakers, and this concludes our plenary session, and we can now transition to parallel. Thank you.